There are different infinities. Remember that saying that an infinite set A has the same number of elements as the natural numbers is the same as saying it is possible to write out all of the elements of A in an infinite list. So saying that an infinite set A does not have the same number of elements as the natural numbers is the same as saying that it is not possible to write the elements of A in an infinite list. Now, both the natural numbers and the power set of the natural numbers are infinite sets. So if we can show that their number of elements are different, then there are different infinities. And so that's what we're going to do. We're going to show that the cardinality of the natural numbers and the cardinality of the power set of the natural numbers are not equal. So they have different numbers of elements. And so then you will see that there are different infinities. And so our goal in all of this is to show that it is not possible to write out all of the elements of the power set of the natural numbers. So let's start by choosing any infinite list of elements of the power set of the natural numbers. And remember, elements of the power set of the natural numbers are subsets of the natural numbers. Remember, the power set of the natural numbers is the set of all subsets of the natural numbers. So let's start. Choose any S1, S2, S3, S4, S5 in the power set of the natural numbers. Now notice that this is an infinite list. That's that little dot, dot, dot at the end, right? That's what that means. It's an infinite list. Now let's take a moment, let's look at an example to help us wrap our minds around what this list could look like. So, for example, let's say that S1 is the subset of the natural numbers 0, 2, 5, 9, 14, etc. And now think about this, right? This has an infinite bit string representation. This has the infinite bit string representation like so. My ones got a little long there. This like this. Okay, those look more like ones, I think. All right, and S2, what could that be? I don't know. Let's just choose a couple of random natural numbers. Let's say 5 and 7. Let's say S2 is the set containing 5 and 5, 5 and 7. And this set, the set containing 5 and 7, has the infinite bit string representation. Let's see. 0 is not in there. 1 is not in there. 2 is not in there. 3 is not in there. 4 is not in there. 5 is in there. 6 is not in there. 7 is in there. And so on. Let's see. What should we pick for S3? How about the odds? So we have 1, 3, 5, 7, 9, 11. And so what would the infinite bit string representation of S3 be? Let's see. 0 is not in there. 1 is. 2 is not. 3 is. 4 is not. 5 is, 6 is not, 7 is, and so on. Let me give myself a little more room. Let's see, what about S4? What should we make that into? I don't know, let's make it into the empty set. That'll be easy. 0, 0, 0, 0, 0, 0, and so on. And S5, what should we make that into? Okay, let's make it into the natural numbers. That'll be easy as well. And now remember, this is an infinite list of elements of the power set of the natural numbers. So this goes on forever. And so on. Now, by the absent bit string rule, there is some S in the power set of the natural numbers that is not in this infinite list of infinite bit strings. By absent bit string rule, there is some S in the power set of the natural numbers not in this list. And see, that's the point. The absent bit string rule guarantees that any infinite list of infinite bit strings does not contain every possible infinite bit string. And since we can represent, and we've seen this already, since we can represent all subsets of the natural numbers with an infinite bit string representation, a unique infinite bit string representation, the absent bit string rule guarantees us that no matter what we pick for a list of elements of the power set of the natural numbers, there's going to be some element of the power set of the natural numbers not in the list. And that's true of any infinite list of elements of the power set of the natural numbers. So this was just an example to help you get your mind wrapped around what we were actually doing. But that's true of any possible list of subsets of the natural numbers. So no list of elements of the power set of the natural numbers contains all elements of the power set of the natural numbers. So no matter how hard you try to list out the elements of the power set of the natural numbers, you're never going to be able to do it. The absent bit string rule, which we've proven, shows that this is impossible. So it's impossible to write the elements of the power set of the natural numbers in a list. So the cardinality of the natural numbers is not the same as the cardinality of the power set of the natural numbers. And that is our proof of this fact. Oh, I didn't write proof, did I? Let me write that here.